All right. Thanks very much for having us today. Hopefully you can hear me all right. Yeah, as Randy said, this is kind of something a little different. In the midst of our big cold air outbreak, we thought we'd take you back into some supercell dissection, I guess you can say. So we did change the title up just a little bit to the relevance of a low-level storm relative velocity enhancement airstream, which we call the SURVE, in tornado-producing supercells prior to tornado genesis. But we could really say, you know, looking at supercells in general, and we'll talk more about that as we go along. So we'll get into it now, and I'll take the first part, and Aaron will kind of jump in for the second half of the talk. And all right, so this is just a little teaser. So this, as you may or may not be aware, Aaron and I are both on the Central Region TWIP and developing training. He and I more so in the supercell realm. So some of the training that you may have gone through, much of that, at least pertaining to supercells, was developed by Aaron and I. So we've been looking at this stuff for quite a while. And so what you'll see today will make its way into additional modules that'll be coming along, hopefully within the next few months, so that you'll have it in time for next severe weather season. But that'll be part of what we call a TWIP Advanced series, which kind of, you know, again, takes a little bit of a deeper dive into some of the concepts and research associated with supercell tornado genesis. So a little background first. You know, in general, radar training that's available has lagged a lot of the research that's out there, peer-reviewed research from academia and some others. And that's not really anybody's fault. It's just kind of the way things have moved. There's been so many moving parts, as has been alluded to earlier this morning, that it's sometimes hard to get everything caught up to, you know, and maintain that conduit with the research community. So in general, you know, there's a lot that the 88D can do. It is a research grade radar, but of course it's been around for a long time, and especially with the advent of dual-pol, we kind of have the feeling that there's a lot more that can be used or utilized with the 88D than maybe what is typical in warning decision making. So again, especially with dual-pol, we've heard a lot about how it can help you determine precip type, but what it can also do is kind of help you understand maybe thermodynamic properties of downdrafts based on the type of hydrometeor in that downdraft. So obviously some of the TWIP training has started to correct this and kind of catch us up to where some of the research is. But even, you know, some of the stuff that you may have seen with the ZDR ARC, you know, that research has been around for well over a decade. So we're trying to get caught up on that. Also, you know, we've heard a lot about the low-level rotational velocity couplet that a lot of us have, you know, kind of keyed in on as being not necessarily the magic bullet, but you know, kind of just something people tend to trend toward looking for. But what we have to realize is that this doesn't magically appear, and in fact, in many cases, or in most cases, if you get this a well-defined velocity couplet to appear in the low-level slice, the tornado warning is probably too late based on the latest research that suggests that the rotation occurs right near the ground before you'll see it, sometimes in that rotational velocity signature. So what that relates to is, at best, a 0 lead time, but more likely a missed event. But what it can also do is lead to a false alarm, because if you're only looking for that and not addressing the thermodynamic property of the downdraft associated with that supercell, you can have a pretty good VROT signature, but still not get a tornado. And contrary to that, sometimes you don't need a real killer VROT signature to get a tornado. So there's a lot more to be had there. But the main thing is, the high-res modeling and the latest research that's out there, and really has been around for, again, over a decade, suggests, first of all, that tornado genesis is a process. Some of these signatures and stuff we've been trained on, again, aren't just magical. There's a process to getting them to be viewed. So again, in general, research has told us that tornado genesis is driven in part by a downdraft, which originates from the forward flank. We heard a lot, for those of us who have been around a long time, we always used to hear primarily about the rear flank downdraft. Well, latest research suggests that the downdraft is actually originating from the forward flank or somewhere in that interface. Again, as I alluded to, buoyancy must be favorable in that downdraft in order for the tilting and stretching to occur. Positioning of the low-level mesocyclone is also critical based on the work that Markowski and Richardson did back in 2014. And then again, we have to keep in mind that even in supercells, tornado genesis is really a fairly rare event. So what is a SRVE, or a storm relative velocity enhancement airstream? So as I have circled on the little velocity picture here, by definition, I guess the low-level storm relative velocity enhancement feature is best seen inside of 40 nautical miles, as most low-level features are with the 88D. Generally, from what research suggests, when you're looking at the proper area of the forward flank, you want this to be below 1 kilometer. So again, that means, we can't get away from the radar horizon issues, so you're going to need to be fairly close to the radar to see this. It may show up as an inbound or an outbound signature. It depends on your radar viewing angle. Is the storm located north, south, east, or west from your radar? So, and in some cases, depending upon the orientation of the SRVE, it may actually be perpendicular to the radar beam, in which case you won't see it in this presentation as I have it shown up here on the screen. So again, it could be an inbound signature, outbound signature. The main part of this is that it's an asymmetric signature. In other words, it's kind of dominating what you might think of as a rotational area of the supercell. It's really just looking at one side on the back side of the meso. Looking at this particular feature. And again, it's an airstream rather than just a fleeting signature that you might expect to see. So in the upper right corner there, I do have, I kind of switched through various other insets there of the supercell. This particular supercell is the Mayfield, Kentucky EF3 that occurred back in 2016. So in this particular inset is the half-degree KDP. And then this one, of course, is the ZDR that you see in the inset there. And then the circled area kind of shows you where the SRVE occurs in relation to the ZDR. In this case, a ZDR, well-defined ZDR arc. As a quick refresher, those reds and pinks and orange colors represent higher ZDR values, which, because of the oblateness of the raindrop, suggests large drops in that area. So again, we really want to reiterate that this is an asymmetrical feature, which suggests that this is an airstream. It's not it's not just a transient signature that you're going to see appear and then kind of disappear or magically appear. But it does evolve over time, and you'll see this as you have downdraft surges within the supercell, how it changes its orientation. And we won't dive a whole lot into that. Hopefully, as we have time, the advanced TWIP training series will kind of go through that in more detail. But as you'll remember from some of the training in TWIP, and as we'll get into here in a little bit, this particular area of the supercell is pretty important for a variety of reasons. With that downdraft, precipitation downdraft, this particular airstream is adjacent to a buoyancy gradient by definition, which means there is horizontal vorticity generation occurring in this airstream here. And then we'll look at the why it's important to assess the where the convergence happens with the survey under the low-level meso. Again, low-level meso positioning is very critical in the whole tornado genesis process. And this is another case. It's actually from 2013, the Roselle, Kansas tornado. And in each of those cases that I showed, the Mayfield one and the this Roselle storm, these are velocity, storm relative velocity snapshots from about 13 or 14 minutes prior to tornado report, I guess, or what's in storm data. And again, that 13-minute threshold is kind of critical based on what GIPRA goals are. And so that's why this becomes so important, is because we're looking at prognostic indicators so that you can hopefully anticipate when some of this might happen leading up to tornado genesis, and not just in a reactionary sense. So let's look a little further at what's happening in this area where the survey appears. So as I mentioned earlier, there's numerous peer-reviewed research articles that suggest this area is adjacent to a horizontal buoyancy gradient that exists because of the precipitation downdraft that occurs in the forward flank. And then as a result, this area is an area of baroclinic vorticity generation, as noted there by the small little signature there by the forward flank downdraft boundary. So this particular image is adapted from the Rotuno et al. Research back in 2017, where they kind of look at more detail again at what's happening with that descending airstream. This little snapshot of a video done by ORF back in 2014, where they did high resolution simulation of the 2011 El Reno tornado, goes through their simulation of when they dropped little stream tubes through the forward flank region, the parts that make it into what they call the SVC, and then those that actually make it into the tornado. And so you can see as these little stream tubes, as they go further into the cold air of the forward flank, those are the parcels that actually make it into the tornado. So again, the parcels originating along the downdraft boundary are the ones that actually make it into the SVC. And you can kind of approximate that as you're looking at the ZDR arc, but this was really looking more at the low-level mesocyclone. But those parcels that originate from deeper within the cold air of the forward flank, at least by their simulations, are the ones that make it into the tornado itself via the descending airstream. So picking up on that idea a little bit further, Finley et al. These are some graphics from some work that they presented to the Central Region TWIP and some others along the way, but they've identified these same features. Now, these notations that I have included here are my own. These aren't things that were part of their research, but the SVC is shown there by the red trajectories. Again, those that are originating along the forward flank downdraft boundary. But then those that are in blue color there are the ones that are actually originating from deeper within the forward flank that seem to line up with what we're identifying as the survey airstream. So again, this is looking kind of from a northeast or an east to west perspective. If I put up, again, the storm relative velocity image from about 13 minutes prior to tornado genesis from the Mayfield, Kentucky case, we're kind of oriented a little bit differently. So if I were to kind of turn the Finley graphic a little bit kind of on its head, it's kind of hard to follow a little bit there, but hopefully that allows you to see how these kind of airstreams, those that they've identified, not as a survey per se, but from those originating from deeper within the forward flank, line up pretty well with the survey airstream that we're identifying here. So again, if we dig even further into this research, and again, primarily we're looking at tornado-producing supercell storms, and I know, you know, there's the age-old argument about why are we only looking at these big EF5s or, you know, kind of no-brainer type supercells. And I guess the point is that you got to kind of start there first, and then, you know, kind of evolve your research to maybe hopefully identify some of those more cases that aren't so clear. But for the next couple of slides here, we're going to focus on the area in the red box. And again, that's associated with that descending airstream based on research, peer-reviewed research that's out there. So here we're looking at an adapted figure from the Dahl et al. Research from 2014. Just kind of shows you kind of their depiction of, they actually took their simulation and broke it into barotropic and baroclinic vorticity generation. So we're not going to go into that much detail, essentially separating between storm-generated vorticity versus that's being contributed from the environment. But we know from previous research that when it's broken down, most of the, or the greater percentage of vorticity generation actually is storm-generated that produces tornadoes. So again, in this particular area of the supercell, there's continued baroclinic vorticity generation that occurs in the cool outflow. That's descending during as it rotates around the backside of the low-level mesocyclone. What research has found when really doing the simulations, the high-res simulations, is that this vorticity vector gets tipped off the vortex lines, and that actually occurs as a result of the vorticity generation that's happening, which initially is all crosswise, or mostly crosswise, as it's beginning its descent behind the backside of the low-level mesocyclone. Now, if you dive into the research from Dahl et al., you'll find that it is this crosswise vorticity generation, at least in the vertical plane, that actually promotes this tipping, such that the vorticity vector in its descension is tipped tail first, which allows it to reorient that vector into vertical velocity, or vorticity, sorry. And here's kind of a look at that a little further along, as Parker and Dahl took that research and took it a step further to kind of show that in a 3D sense. The critical part here is that as the vorticity is nearing the ground and really making that turn under the low-level mesocyclone, that's where the conversion happens to streamwise vorticity. Whoops, let me go back here. So it's really in this area, and Aaron's part will dive into this a little bit further. So now what? That's kind of always the question I tend to ask, as you know, you go through all this research and then you kind of get the reality check that you are limited to what we can see in AWIPS. You're obviously not able to see downdrafts at all. Rather, you're inferring those from 2D snapshots, right? When you're going through and looking at 88D data. So you can't see downdrafts. You can't see vorticity per se. Again, these are all things that are inferred. And in fact, you can't even see three-dimensional convergence. You're really left with a literal interpretation of velocity such that you're interpreting 2D convergence. So we really need to go back to what we started with, which is that survey feature, the airstream that we've identified via the storm relative velocity enhancement. So at this point, I'll let Randy switch it over to Aaron, and he'll kind of take a review of where we've been and take us a little bit further.
All right, hopefully everybody can see my screen or hear me. But assuming you can, so before we dive into some examples of the survey in the second half of the talk, we are going to briefly pause here to reiterate the key points that John mentioned. And we do this here because we fully understand how potentially overwhelming this more prognostic analysis can seem for many folks, especially as John said, given the much different way of using velocity products with supercells relative to say, legacy low-level rotational couplet intensity assessment, or VROT, that is more diagnostic in nature. So what we're going to look at here to start, if I can get this to advance, let's look at what we know and what John had mentioned. So this survey, we know the storm relative velocity enhancement signature. It is a low-level feature. We're seeing the end stage of a descending airstream. So because of that being low-level in nature, we're not going to be able to see this out beyond, say, 35 to 40 nautical miles. Now, that doesn't mean there are ways to assess, let's say, buoyancy potentially in this survey at farther out, but there's really nothing, say, at 80 nautical miles that's low level anyway. So this is part of your expanding radar toolbox that you may be able to see this directly, you may not. And some of this is going to be dependent, in this case, are you seeing it as an inbound or an outbound signature? That's going to depend on your viewing angle. And you may not even see it that well if the radar beam is perpendicular relative to the survey. Now, you may see portions of it. And in one of the examples I have later, you can kind of still see the survey, even though it's more of a zero isodot, but you can kind of follow the airstream. But as John said, and this is key, if I can get this to advance, this is an asymmetric signature that originates from the forward flank downdraft, wraps around the backside of the low-level meso, and then if processor right, moves underneath the low-level meso. So it's an airstream, not a indication of, let's say, the mesocyclone. It is this airstream that's important. And so when we know that this is an airstream, we know that, foremost, these parcels composing this airstream are acquiring baroclinically generated vorticity as they move rearward from the forward flank region. And so, we may see this airstream ascend briefly, but it's more of this rapid ascension within the outflow that we're following. And we see this end stage, let's say, on the half-degree tilt. And so over time, as John just mentioned, the vorticity vector tends to be less downward inclined than the airstream trajectory. So near the ground, this inclined vorticity vector can be tilted and stretched upward thanks to the position near the updraft, or especially in this case, near the low-level mesocyclone. Now you may say, this is great, but how is this going to help me be able to see the potential for tornadogenesis? Well, the key may be trying to assess where there's turning of this airstream. And specifically, you can kind of assess this through maybe a convergence zone. So in this example from the Mayfield, Kentucky EF3, we can see through this yellow dashed line that there's kind of this area where kind of almost a zero isodot where something's going on with the flow. Now, it may be specifically convergence, but it's more likely we're seeing a turning of this airstream. And that's important because initially, if the blue line represents the airstream, this white arrow is initially the vorticity vector looking more crosswise in nature. And as the research has shown with this downward moving descending airstream, if you can get this turning underneath the low-level meso, you get through what's called the river bend effect, a conversion from crosswise to streamwise. So to illustrate here, over time as that airstream turns more to an east-west or even a northeast to southwest orientation, the vorticity vector is becoming more along that airstream, and in other words, becoming streamwise. And that's important because when this vorticity is then tilted and stretched into the vertical, now we have a source of near surface vorticity that, in case of tornadogenesis, where we know it's a bottom-up process, we have that source of near surface vorticity that can help induce tornadogenesis, assuming the other components are there. Now, you could also say, well, is this a feature that only is illustrated or seen within tornadic supercells? The obvious answer is no, in that we know most supercells will illustrate some semblance of a forward flank downdraft. So it's not a feature that's only going to show up in tornadic supercells, but there is a difference, and this is where the turning becomes important. So in this case, this is an event, actually we've illustrated frequently within our TWIP training from October of 2017, very good classic non-tornadic supercell. But you'll notice it has a similar looking inbound velocity feature on the half degree. However, although we don't illustrate where the low-level meso is, if you kind of look at the inset of the reflectivity, you can see that this inbound signature, instead of turning like the previous case, is blowing right past it. In other words, more than likely we have too much negative buoyancy within this airstream. And so you can kind of see how the fine line is surging well south of even the tip of the hook. And so just as a side note, there was also several ZD arc disruptions in the dual-pol data, which tells us there's a lot of wet melting hail that's adding negative buoyancy that probably produced a significant momentum surge to where that turning was not able to occur. So even though in this case, similar to the Mayfield case, we do have baroclinically generated vorticity that starts off crosswise dominant, because we didn't get that turning, the all-important conversion to streamwise likely did not occur, and so that vertical vorticity near the surface remains near zero. Now, obviously, this kind of highlights some important aspects, as we've all seen non-tornadic supercells with strong, low-level mesocyclone, rotational values that look similar to tornadic, but were maybe a little perplexed why that storm didn't produce. Well, this also highlights how complex tornadogenesis is, and that a buoyancy aspect of this airstream can inhibit genesis. On the flip side, you may have a more modest looking low-level mesocyclone where this turning occurs, and that's enough through tilting and stretching of what's now streamwise vorticity to induce genesis. So this is where we shouldn't get too caught up in rotational values in an absolute sense when it comes to predicting or anticipating tornadogenesis. So with that quick review, we're going to look through a couple of examples, and they're both from the Dodge City area. So since I'm talking, guess what? We're going to look at Dodge City cases. So this first one, John briefly mentioned this. This was the 2013 Roselle, Kansas EF4 tornado. So as already highlighted here, you can see there's this strong inbound, and we've got the circle also showing where that is in relation to the reflectivity. Now, we just talked about looking for possibly this zone of convergence as an indication of turning. And we do see a pretty strong decrease in the inbound velocity there that is giving us an indication that this airstream is now turning. Of course, we want the positioning to be underneath the low-level meso so that if we do get conversion to streamwise, there's enough dynamic lift to stretch and tilt that vorticity into the vertical. Sure enough, when we look up at the 1.4 tilt here to kind of assess our low-level meso in that 3,000 to 6,000 foot layer, sure enough, it is lined up perfectly in that zone. So at this point, I think we're around 10 minutes before tornadogenesis. This should give an individual strong confidence that tornadogenesis is increasing, or is, I almost say likely at this point, assuming other factors are in play. So again, we know from the research that this turning is that conversion to streamwise vorticity. And it's not going to be completely streamwise, but it's going to go from crosswise dominant to streamwise. And so again, we get this ultimate tilting, and in this case, we know there was a fairly long-lived EF4 tornado. So this last case, and this is one I talked about actually in the August guest speaker series, highlighted more of the dual-pol data, but we're going to jump back to this case. And for those that didn't see that talk, some of these slides may be new for you, others it may look similar, but we're going to highlight the survey in this case. And so we're going to start off, this is about T-minus 15 minutes before tornadogenesis. Now what makes this case unique is there's no hook echo, There's no half-degree, low level couplet that you're going to be able to assess here. What we can see through both kind of a hint of a fine line, but more of in the velocity, we can see this downdraft boundary. But we're going to focus in two areas. Initially, we see east of, or kind of east-southeast of the town of Fowler, we see this divergent signature. And that gives us an idea that there's probably a new downdraft occurring in that region. And although the reflectivity is not high, we can also see the start of a ZD arc. So that gives us confidence that this is more than likely a new forward flank downdraft. But more importantly, and not going to show it at this point, but we know that there is a new updraft, a new mid-level mesocyclone existing near Meade, or actually just east of Meade, Kansas. So what we look at, we see this stronger outbound signal near Meade, and that kind of matches what we see within the conceptual model, such as this simulation from ORF. So we can kind of check that box, but more importantly, since we know this can exist in tornadic and non-tornadic, do we see an abrupt decrease in the winds, a kind of a convergence signal that may indicate turning? And hopefully you notice, yes, we indeed see this area where there's a pretty good indication that this airstream may be turning. So you say, well, that's fine, but I need confirmation of this. Well, we'll jump ahead. We're now within the window where we're looking at a 13-minute lead time, but still, we can still get some decent lead time at this point. So features don't change in the reflectivity much. We continue to see this divergent signature near Fowler, indicating more than likely a new forward flank downdraft. I also see a ZD arc, as you can see in the lower left corner. But we also see this velocity, this storm relative velocity enhancement, moving toward this region east of Meade and then decreasing. So once again, pretty good indication, this convergence signal. So ultimately, we need to see, just like we looked at with the Roselle case, is the low-level meso, or is there even an indication of a low-level meso in that region? And while the reflectivity presentation is not great, when we jump up to the 1.3 tilt, we indeed see a weak cyclonic circulation. And this goes back to what we talked about. Don't get fixated on absolute values. The trends in velocity in relation to the mesocyclone can be all over the place. Before tornadogenesis, it can be an upward trend, it can even be a downward trend, it can be steady. The key, though, is from a prognostic perspective, we're trying to look at what gives us lead time, what gives us the ability to anticipate. And so in this case, we're seeing this airstream, looks like it's turning, and it's directly under this developing and likely intensifying low-level mesocyclone, which, again, we can utilize the ZDR arc to kind of say, yep, everything's in place for that meso to intensify. So this would have been the time to issue a warning. But if you're not convinced, we'll jump ahead all the way to tornado time. And so while the reflectivity presentation gets a little better in the forward flank, still no great hook echo, yet we already have a tornado ongoing. We still continue to see this velocity enhancement. It's also continuing to kind of converge there southeast of Fowler now. And the low-level meso is in that general region. It's intensified a little bit. Presentation not the greatest, but it's still there. And this is 2 minutes after tornadogenesis. So you could say, well, is this feature present even during a long lift? Because this was an EF3 tornado that existed for almost 45 minutes. And so if we jump all the way to T plus 31 minutes, now I'm jumping up to the 0.9 tilt because we're close enough to the RDA that the half degree has a lot of ground clutter issues. But we continue to see this kind of outline of this downdraft boundary. We also continue to see this survey. It's moving into that area where the low-level meso is, and we see a good indication of turning. Now, this was a cyclic supercell, so it obviously, this tornado eventually ended, but the next one, we'll jump 2 minutes prior to tornadogenesis. Once again, we see this same signal. Now, I will also highlight, as John mentioned and I reiterated, sometimes the survey is going to be more perpendicular to your beam. So notice you see this kind of strong inbound on either side of what's kind of almost a zero isotop. That's still, even though you don't see the magnitude per se, that still gives you a strong indication of this airstream that's coming from deeper in the forward flank region, moving through, turning, and then obviously the low-level meso was tilting and stretching what is now a more streamwise dominant vorticity vector. So to finish up here, just some take-home points. I know we've thrown a lot at everybody, and hopefully the illustrations can kind of help you see this. Again, this is an asymmetric airstream originating from the forward flank. This isn't the meso. This isn't some big circulation. This isn't, we're following an airstream, but this airstream has significant importance. And so we know this airstream is directed toward the low-level mesocyclone, even as it's developing. As it descends, we know due to the buoyancy gradient that we're going to see bare clinically generated vorticity, and it's going to be mostly crosswise in nature. And some of this has been known really for years. I mean, dating back to even Vortex 1, we know that there's this bare clinically generated vorticity that's very critical to tornadogenesis. But in this case, we know it's mostly emanating from the forward flank. So again, this vorticity is mostly crosswise initially. If we get that 2D convergence, in other words, it's turning, we see this conversion to streamwise, and that's through this river bend effect. So that's where, as a forecaster or as a warning decision met, you're going to be looking to the best of your ability for this potential area of turning. Now, if you don't see that, this isn't a magical process that, it's going to be 100% all the time. And we'll talk about that in a second. But if you see that turning and everything else, being decent, your odds of tornadogenesis increase. And so ultimately, you get that turning, that vorticity is tilted in the vertical and stretched, and now you get the bottom-up process of tornadogenesis. So what this isn't, just like any radar analysis, there's no magic bullet here. So there's no silver bullet, and really nothing like that exists. Tornadogenesis in supercells, despite some common misconceptions, is an extremely complex process and is actually fairly rare, which probably explains why historically we've had fairly high false alarms, because we're assuming that simple existence of a low-level meso is good enough. Well, obviously, as this illustrates, no, there's other things going on. And so, again, this feature is apparent in non-tornadic storms, and so we've got to use the features that we can assess to try to help determine if that turning is occurring. And so the ADD gives us these 2D snapshots of base moments. And so we have to infer things. So we can't directly see, the downdraft buoyancy, for example, but we can infer things. We can't necessarily see the nature of the vorticity. We have to infer that through things such as the turning. And of course, we're never going to solve, horizon issues. So anything really over a kilometer is likely not the survey. That may be, as John detailed, you're seeing an ascending airstream such as the SVC. So it can get confusing, but you have to put, the assessment of where I'm looking in terms of above ground level and understand, okay, this airstream is more than likely descending versus ascending. And so all of this, there's going to be subjective analysis, and we're never probably going to get away from that. But this tool, it's a different way to assess the potential for tornadogenesis and using the velocity in a much different way rather than just waiting for couplets to form. And so that's all we have. I appreciate everybody watching this. Hopefully this was useful and educational for everybody. But I don't know if we have any time for questions, but I guess John and I can take whatever time we have to answer questions.